Hello everyone, welcome to my YouTube channel. So in this class, I will teach about the chemical shape value of the organic compound in the NMR spectrum. So now I will take the example of the 1,6-methane 10-aniline. So this is the structure of this molecule. So here the NMR spectrum indicates the presence of the induced ring current as the peripheral hydrogen atom are dishielded, having the delta values 7.20 ppm, and the bridging methyl hydrogen are strongly shielded with the delta value at 0.5. So thus the compound is undoubtedly planar and aromatic. The 14 pi electron containing bridged aniline dipropyl dihydropyrin is aromatic, is 4n plus 2 system, and the same anisotropy as that of the benzene expected here. So nuclei located over the face of the ring are shielding zone. Those on the periphery are shielded. The ring hydrogen give resonance signal of the range of 8.0 and 7.8 ppm as expected from the desired location, and the two N profile groups are structurally equivalent, and they are the two to rotate over the face of the ring, and one above and one below. So on the average, all the profile hydrogen are shielded, and with this innermost methylene being most affected, so these negative chemical shift noted here indicates the resonance occurred at a higher field than the TMS reference signal. So that means, so first in this example, it is the 1,6-methanoline. So here it is a it is a pi in this molecule. That is the aromatic molecule. So here the bridging here, this is the bridging methylene group. So this bridging methylene group has a delta value is 0.5, and this aromatic region, this hydrogen has the delta values at 7.2 ppm. So that is because that these all hydrogen are in the ring, are in the plane of the benzene ring. So that is these hydrogen. So these hydrogens are in the dishielded zone. So due to the ring current of the aromatic ring, so these hydrogen are in the dishielded zone. So this is give the value 7.20, and this methylene group is a bridged. So here this is the these hydrogen atom are in the upper side of the this molecule, plane of the molecule. So this is in the shielded zone. So that's why the hydrogen have the delta values as 0.05 ppm. So now for this case, this molecule is a dipropyl dihydropyrin. It is also a aromatic compound. So here total 14 pi electron are present. So it is a aromatic compound. So here all these hydrogen are in the dishielded zone in the plane of this molecule. So all are have the expected delta values at 8.0 or 8.5, but this profile was this two N profile group. These are in the dishielded zone. In the one profile group is the this is in the upper side of the ring, plane of the ring, and this is the lower side of the ring. So this is the shielded region. So here this proton has the values of the minus region, and this CH2 is most affected because this is the most near to the shielded zone, so it is more similar and gradually when the increase of the length, these hydrogen are, are away from the shielded region, so this is comparatively less shielded, so it has the value point -17 and -0.06. And a remarkably characteristics of the aniline is the anti-aromatic foreign pi electron system at the anisotropic in the opposite sense as their aromatic counterparts. A dramatic illusion is the fact is provided by the dianion derivative of the above bridge aniline. So this is the dianion formed by the addition of the two electrons. So it is 16 pi electron system in the dianion form. So shielding zone generates the outside of the ring, that is in the plane of the ring. So the ring hydrogen has the generates upper shift, and the center of the ring creates a deshielding zone. And hydrogen of the propyl groups are shifted downfield. So the innermost ethylene group give 2.20 ppm, and the signal of the adjacent ethylene and methyl hydrogen and have the unexpected largely chemical shift. So among these two compounds, this is the aromatic one and this is the anti-aromatic one. So it has total 16 electrons. So and in the aromatic compound, the ring current are the ring current that create the deshielding zone in the plane of the molecule, and shielding zone is created in the upper and lower side of the ring. For this anti-aromatic compound, this situation is opposite. So for the anti-aromatic compound, the shielded zone is created in the plane of this molecule, and the deshielded zone is created in the upper side and lower side of the plane of this molecule. So for this, so if this is the anti-aromatic molecule. So here this propyl group is hydrogen are in the deshielding zone, in the strong deshielding zone. So here the chemical value is the most deshielded. So in have value 2.2, 22.2 and 12.6. So this is the opposite of this case. So now we look about the critical comparative studies on the some simple compound with the reference of the diamagnetic anisotropic effect. So let's the example of the formaldehyde, and so formaldehyde have one type of proton. So it has the chemical shift value is 9.60, and it is only one chemical shift 9.60. And for the and also for the benzaldehyde, this has total 1, 2, 3, 4 types of hydrogen atom. So it has 4 signal on 9.88, and another in the aromatic medium 7.89, 7.64, and 7.63. So for the benzaldehyde contains 4 sets of non-equivalent proton. So among them this aldehydic proton absorb most downfield shift at delta value is 9.88 than of the formaldehyde. So due to the combined electron effect and diamagnetic deshielding effect of the carbonyl group as well as the aromatic nucleus charged as a benzylic proton. So here the formaldehyde had the delta value is 9.60 and for benzaldehyde is 9.88. The benzaldehyde is a more downfield due to the anisotropic effect of this Kc double bond, CO double bond, and also the inductive effect of the this benzene ring, and also the benzylic position of the these hydrogen in a benzylic position, so giving more downfield. And also we know that due to the ring current effect, the aromatic proton oriented such that it content in the plane of the benzene ring is in the diamagnetic descending zone, and so high downfield shift at 7 to 8 ppm. Now the larger descending is provided by the proton in the aromatic compound that are ortho to the carbonyl group, and the larger descending effect experienced by the ortho group by the minus side effect of the carbonyl group along with the desilting effect of the anisotropic carbonyl group. So the spectrum of the benzaldehyde shows that the two ortho position formula is 7.89. The high down switches on the other three proton absorbed at 7.65. So here for the benzaldehyde case, the ortho proton, the aromatic proton normally in the descendant zone in the plane of the compound. So here is normally in the descendant zone, but for the ortho proton, the chemical shift value is 7.89 compared to the meta and paraproton. So ortho proton is a more in descendant zone due to the because of the one reason is the minus I effect of this carbonyl group and also the and the combined effect of the combined minus I effect of the carbonyl group and the anisotropic effect of the C double bond O. So that's why the ortho group is a more descended compared to the other. So that's why it's got the more descended value 7.89 and the meta and para are the far away from the carbonyl group. So that's why they got the delta values at 7.65 and 7.89. So let us, an example is the acetophenone. So acetophenone, it has one set of compound, one set of proton. So all these 6 hydrogen proton are equivalent. So it will give the delta values at 2.13 ppm. For the acetophenone case, it has (2.50 ppm) and aromatic region and the distillate zone to 7.94 and 7.53. So here all the ring protons of the acetophenone are in the distillate because of the ring current effect of the benzene rings. And however, the orthoproton are further distillate with respect to the metaproton because of the addition distillation of the carbonyl group. Similarly, protons of the carbonyl methyl group presents at higher delta values with respect to the normal region as in the acetone. This was because the additional descending level of the aromatic nucleus. So same for like the benzaldehyde or same reason happened. So orthoproton is the more descendant due to the minus I effect of the desilting effect of the carbonyl group, and also here the CH3 is normally have higher ppm compared to the other CH3 due to the desilting minus I effect of this phenyl ring. So now the consider the NMR spectra of the cyclopropane. So cyclopropane as follows: cyclopropane has all the hydrogen proton is in the same chemical environment, so it has one sets of protons, so it will give the value is 0.22. So eventually by the protons of the cyclopropane system appear expressed as high field above the usual range of the methylene groups, even above the range of the most of the methyl group. In the cyclopropane itself, there are cis vicinal CH bonds are able to conjugate with each other just as a pi conjugation. The cyclic 6-electron conjugated system thus set up the ring current. So the proton following the diamagnetic desilting region of the magnetic field induced by the ring current. So the cyclopropane region at 0.22. So here the cyclopropane, the proton are in the more shielded region compared to the other methyl or methylene group due to the because in the cyclopropane there as well three vicinal CH bond are able to conjugate each other just as the pi orbital conjugation. So here this pi orbital, so this is the cyclopropane. So here the pi orbital. So these 3 pi orbital can conjugate to each other to produce a ring current, and also so here the shielded region are created on the above and below of the cyclopropane ring, and the descending region is indicated in the plane of the cyclopropane ring. So that's why these all the hydrogen photon are in the shielded region of the cyclopropane due to the ring current. So that's why it is in the upfield compared to the other methylene or other methyl group. So now that any group is strictly held above and below of by the plane of the aromatic nucleus will be abnormally shielded because of the ring current. So let us close look at delta values of following compound. So that means any group are sterically held above and below of the plane of the aromatic nucleus will be abnormally shielded because of the ring current. So this is the 1,8 paracyclopentane. So here this methylene group delta value at 0.3, 0.9, 0.13, 0.25. So the methylene photon of at C1 absorbed at normal benzalic region due to the diamagnetic shielding of the nucleus at 2.5. So this methylene photon it's come as a so here the C1 photon is normally come at the 2.5 to show the descending effect of the benzalic region, and on the moving from C1 to C4 the methylene photon as well as normally uphill. This is due to the fact that the central methylene groups are the held rigidly just above the benzene ring, which is diamagnetic shielding zone of the nucleus. So this photon is in between the diamagnetic shielding zone. So that's why this is the most upfield compared to the other. So thus the methyl photons of the C4 show very upfield at 0.3 as the methylene photons of C3 and C2 are in the partial shielding zone of the ring currently. They are present in compared low field 0.9, 0.13 respectively. Again, the methylene photon in between the two benzene nuclei at the mass downfield 3.18 in the normal benzelic region due to the combined diamagnetic anisotropic effect of the shielding effect of both the aromatic nucleus. So this benzelic CH2 is come as 3.18 due to the combined descending effect of this pH ring. So this is come at 3.18 ppm. So next, compare the NMR spectra of the cis-stabile and the trans-stabile. So this is the NMR spectra of the cis-stabile and the trans-stabile. So here we partially interested about the here we interested in the vinylic, these two vinylic photons and the orthophotons. Cis-stabile and trans-stabile are geometrically isomer. So in the trans isomer, each vinylic photon lying in the plane of the two phenyl rings and thus shielded maximally by the normal region, and the diamagnetic anisotropic effect of the two pH ring and the generation at 6.95. Cis isomer, two phenyl rings are the slightly titled due to the steric region, and here is the following structure. As a result, two vinylic photons don't experience the full diamagnetic anisotropic effect of this phenyl ring, so shielding is reduced here to the vinylic photon system is a higher 6.49 compared to the trans isomer. Thus, from the difference in the chemical shape value, two geometrical isomers can be distinguished from each other. Another point to be noted that in the both isomer, orthophotons are shielded more with respect to the meta and para, which is due to the combined diamagnetic anisotropic of the both aromatic nucleus and carbon-carbon double bond. So here, in the cis-stabile and trans-stabile, this vinylic photon in the trans-stabile as the more can be descended because here due to the combined effect of the two phenyl ring. So that's why these two trans isomer has a more descended value. But for the cis isomer cases, due to the steric effect, these two phenyl ring are slightly tilted. So here fully descending so here the fully diamagnetic anisotropic effect is not observed for these two hydrogen. So here these two hydrogen are little bit upfield. So that's why these two hydrogen in the little bit upbeat compared to the transition isomer. So by the NMR spectroscopy, we can identify the between the cysteine beam and unstable beam. So now this consider these two structural isomer, alpha tetralone and beta tetralone. So for the alpha tetralone, we can identify these two isomer by NMR spectroscopy. In case of alpha isomer, 3 aromatic protons C5, C6, and C7 are expected to appear normal aromatic shielding region at 7.3, but this isomer contains an aromatic proton at C8, which is ortho to the carbon functionality. So it is expected to resonate further lower field at 8.0 due to the anisotropy of the carbonyl group along with the aromatic nucleus. Now for the alpha isomer, the proton at C2 being ketomethylene proton appear at 2.62 due to the combined gamma-ray isotopic effect, both aromatic nucleus and the carbon oxygen double bond along with the minus I effect of the carbonyl group, while the proton at C4 being benzylic in nature, thus containing the electron carbonyl group, also expect the resonance at 2.60. So here for this alpha tetralone case, these hydrogen are in the dishielded region. So this has the this dishielded region. So this has the downfield, and this ortho to the this carbonyl group is more dishielded. So that's a more chemical dishielded due to the dishielding anisotropic effect of the benzene ring and also the carbonyl group. So here it is dishielded 0.7.290, and here this H2 is in the benzylic position. So it is a chemical symbol of 2.89, and this has more dishielded compared to the this is 2.90 due to the minus I effect of the benzene ring and the minus I effect of the carbonyl group. So but in case of the beta isomer, the beta isomer aromatic protons and C8 expected to appear in normal aromatic dishielding region around 7.25. Thus is like unlike the aromatic proton and C8 in case of alpha isomer, as in the isomer that proton is further lower field at 8.0 due to the anisotropic effect of the carbonyl group along with the aromatic nucleus. Thus, in the beta isomer, all the 4 aromatic protons expected to appear the region at 7.25. However, in the beta isomer, the proton C1 being both benzylic and ketomethylene in nature, so therefore it expected a region at the 3.60, while no such proton in alpha C4 in benzylic position expected to appear normally in 2.50. Now, so we can distinguish with this alpha isomer beta isomer. So here this CH2 group is in the benzylic position, or also in the due to the anisotropic dazzling effect of this carbonyl and benzene ring. So this is much lower compared to the this alpha dishielded compared to the alpha isomer. So it is 3.71 region. So thus the mainly the presence of the absence of the different downstream proton in the co-isomer at C1 and C8. This C1, and this C8 we can distinguish from each other. Now how the hydrogen bonding can affect the chemical field value of a in the NMR spectroscopy. So on the other than carbon proton attached to the other heteroatoms such as oxygen, nitrogen, sulfur are also known as the exchangeable proton. Functional group exemplified by these are the alcohol, phenol, carboxylic acids, enols, amines, amide compound. Proton associated with these functional group are commonly considered the active hydrogen. So that means the hydrogen connected to this alcohol, phenols, or carboxylic, this is the exchangeable proton. That are the proton. This is the active hydrogen. So NMR spectra, such proton depend on the extent of the intermolecular hydrogen bonding, the rate of the chemical extent, a hydrogen atom involved in the hydrogen bonding. So in the NMR spectra, this such active hydrogen is exchangeable, and so a hydrogen atom, a hydrogen may involve in the hydrogen bonding in the sharing its electron with 2 electronegative element. As a result, since such proton dishielded and come close to the regenerated lower field. So that means when a hydrogen atom, it is a hydrogen bonding with this with the two electronegative atoms. So that's why it's share its electron. So that means in that hydrogen atom has a low electron density in this environment compared to the other. So this hydrogen is in the descended region. So that's why this comes as a downfield shift compared to the normal hydrogen atom. So now when water is taken as a very dilute solution in CdCl3, hydrogen bonding is at a minimum for OH group. The proton comes up with 1.5. However, in the droplets of water suspended in CdCl3, the molecules are hydrogen bonded intermolecularly and they come at the 4.8. The presence of the exchangeable protons of OH group can be indicated by the shaking the solution of the compound is molecular D2O because of the rapid equilibrium of the exchangeable proton with the deuterium. In presence of D2O, the initial proton are replaced by D. So then the original signal OH disappears with the complement appearance of a new signal 4.79 corresponds to the generated signal OHD. So that means in the alcohol, when we take the D2 as a solvent, so this OH is exchangeable by OD. So when this OH comes as 2.0, but when this the OH is but here this OHD comes as 4.79. So experimentally, one simply added a drop of heavy water to chloroform dissolution of the compound, runs the spectrum again. The result is the exchange is displayed above. The number of exchangeable photons can be estimated by reasonably accurately from the spectrum due to the above equilibrium. So we have pointed out that the hydrogen atom involved in the hydrogen bonding is sharing its electron with two electronegative atoms. As a result, its charge photon is decelerated and come into the resonance at lower field. Eventually, on the dilution of the extent of the intermolecular hydrogen bonding, hydroxyl proton will decrease and consequently we do expect the upfield shift of that proton in the NMR spectra. So the NMR signal of the phenolic proton and defined dilution of phenol in chloroform D4 are shown in the following diagram. So that means in this spectra, where this phenolic, so that means as a result, so when the hydrogen atom occurs, this is in the descended region. So that's why the chemical shift value is more downfield. So in the hydrogen, if you in extent of intermolecular hydrogen bonding is decreased when you dilute the solution. So that's case the extent of hydrogen bonding is decreased. So here when the 100% phenol is present, so that's why this give at 7.45 region. When where we concentrate is lower, so that case the extent of hydrogen bonding is decreased and the NMR descended it comes as a shielded upfield shape. So obviously it is expected not because of the favor hydrogen bonding, the dynamic association, the hydroxyl proton of the carboxylic acid is expected to display a significantly downfield of other function. So strictly for a typical acid appears as a 10 to 13 ppm and is open broader than the other signal. The spectra shown below for the chloroacetic acid is typically example of. So here this chloroacetic acid, this OH comes as a 11.4. So intermolecular hydrogen bonding, particularly those defined in 6-membered ring, generally display very low field proton resonance. At the same time, there is no dilution effect on the intramolecular hydrogen bonding. So, however, we point out that the dilution by extent of intermolecular hydrogen bonding hydroxyl group decrease, thus the NMR spectral studies can be utilized to distinguish the intramolecular hydrogen bonding from the intermolecular hydrogen bonding. Now, in case of the salicylate, the orthoisomer of the hydroxyl benzaldehyde can be formed intermolecular hydrogen. As a result, the phenolic OH group becomes highly dissociated and secreted 10.95. But on the other hand, the parahydro. On the other hand, the para-hydroxybenzaldehyde, the phenolic OH group appears at 6.0, is moderately concentrated solution. Now, with increased dilution, the solution delta value of OH proton of the para-hydroxybenzaldehyde shifts upward due to decrease in the hydrogen bonding 4.5. But this is not case of salicylate. The position of the signal remains unchanged with the extent of the concentration of the solution because of the intramolecular hydrogen bonding. So, between these two molecules, we know that hydrogen bonding will affect the chemical shift value. So in the salicylate and the para-hydroxybenzaldehyde. So for the salicylate, there is the intramolecular hydrogen bonding, and in the para-hydroxybenzaldehyde, there was a intermolecular hydrogen bonding. So dilution effect will affect the hydrogen bonding in the para-hydroxybenzaldehyde, if not affect the hydrogen bonding on the salicylate. So when we dilute the solution, the chemical state value of this OH proton upon dilution, the intermolecular hydrogen bonding will affected. It will decrease. So that case, it will come upfield. But for the salicylate, the dilution have no effect on the hydrogen bonding, so it remains as a downfield value at 10.95 upon the dilution. So that's why in this way we can by the NMR spectroscopy we can distinguish between the inter and intramolecular hydrogen bonding of a molecule. So now we will discuss about the intensity of the signal and the number of photons. So we have obtained a series of absorption peaks representing the photons in the different chemical environment. So very nearly the same energy for a given spin transition is involved for each photon in the molecule. So the magnitude or the intensity of the NMR resonance signal is displayed along the vertical axis of the spectrum. Nowadays, it is measured by area, the impulse of the signal. So we have found out at the beginning that under the ordinary condition, magnetic field, there is a very slight excess of nuclei in the lower spin state. The nuclei take up the Boltzmann distribution, but finite excess of the nuclei in the lower energy state obviously give rise to the next absorption energy in the radio frequency region. Eventually, the more the number of nuclei in the lower energy state, the higher will be the intensity of the NMR signal. Thus, the following two factors are responsible. Thus, the following two factors are responsible for getting the high number of nuclei in the lower energy state. So, by increase the operating frequency of the instrument, if you increase the operating frequency of the instrument, the energy difference between these two spin states increases, and consequently, the Boltzmann distribution indicates that it causes the increase the excess nuclei at the lower spin state. Now, it is clear that why the modern instrument has been designed to increase the higher operating frequency. So that means the peak height, the intensity of the NMR spectra, we can increase by the increase the operating frequency of the instrument. So if you increase the operating frequency of the instrument, the energy difference between the two spin states is increases. So consequently, the Boltzmann distribution indicates that it increases the excess of the nuclei at lower spin state, and the second way by increasing the concentration of sample. So eventually, a small or dilute sample will give weak signal, and the doubling or tripling the sample concentration will increase the signal strength proportionally, as then the number of nuclei in the lower energy state will increase proportionally. These concepts can equal the quantitative estimation of total the equilibrium. So that means if we increase the sample concentration, that will increase the intensity of the sample. So let us consider in the case of pentane 2,4 diol. So it is in the keto form, and when it is in the enol form, this is structurally equivalent enol form. Obviously, this compound exists in a keto-enol rotameric form as well inside the structurally equivalent enol form. The NMR spectra of this compound as neat liquid as follows. So in the NMR spectra of the pure liquid, sharp signal from both keto-enol rotameric are seen. The chemical shift value of the hydrogen bonded hydroxyl proton had come at 14.5. So this hydrogen come as a 14.5. Exocyanic downfield, as expected, is a 6-member ring is formed to the intermolecular hydrogen bonding is formed. The compound shows in the presence of the vinylic protons delta W is 5.0 ppm. At the same time, the compound shows the presence of methylene group whose delta W is around 2.6 ppm. Eventually, the methylene proton and the present in the keto form, where the vinylic proton is present in the enol form. Thus, from this assignment as follows, we conclude therefore that the rate of which the conversion of ketotomer to enol tautomer vice versa is slow compared to the inherent time scale of the NMR spectroscopy. This is reasonable as there is no catalytic action or acid or base during first tautomer exchange. So upon this study, nothing intensity of the signal for one vinylic proton and two methylene proton, we can also generalize that the percentage of enol content is higher. However, in the NMR spectra, there is a most important observation regarding the signal of the methyl group. Point to be noted that if we consider the system is totally, there are 3 types of methyl group being a keto form. 2 methyl groups are equivalent. In the enol form, there are 2 types of methyl groups. One ketomethyl and other allylic methyl group. But in the NMR spectra, there are 2 signals for the methyl group. Obviously, if 2 structural equivalent and enols are solely interconverted, so we should expect to see 2 methyl resonance singing associated with each other. One form is the allylic methyl and one form is the methyl ketone. Since only one strong methyl signal is observed, we must conclude that the interconversion of the enols is very fast, so that the NMR experiment detects only a single time average methyl groups. The chemical shift of the methyl groups of the enol form with the higher intensity is absorption at 2.05 and the chemicals of the methyl group lower intensity at 2.4. Now the integral signal of the same number of protons as those for CH3 group in the 2 tautomer are 5 to 4.21, indicating that the proportion of ketone is 16% and the portion of the enol is 84%. Thus, we have a whole assignment for the respect of the pentene alpha diene neat liquid. So, from this NMR spectra, we can calculate. The motive is that we can calculate the percentage of the keto and enol form of this keto and enol form of this tautomerism. So here these 2 methyl are equivalent, so that comes as 2.24, and here these 2 methyl in the enol form is come as a 2.50. So upon integration, we can cut the ratio is 4:2.1. So that means the 60% enol form keto form present in the solution and that 84% enol form present in the solution. And also here these 2 here it is in the methylene proton, and here is the vinylic proton. So here it comes as a 3.60, and here it is a methylene vinylic proton, so it is more downfield, so it is come as a 5.50. So that's why we can calculate the percentage of keto-enol tautomerism in the molecule by the simply integration of the number of protons in the NMR spectrum. So thank you.